Welcome everybody. My name is Rightus Kestrip and I'm the CIBSE Auckland Chapter Chair. Our technical presentation today will be on Filtration and ISO 16890. We're joined today by John Brock from CAMFIL to present the latest filtration guidance and how to reduce the risk of airborne contamination in buildings, which is a hot topic at the moment. Before I introduce John, I'll briefly run through the latest from CIBSE. CIBSE latest technical memorandum TM67 is out now. It draws on expertise from across the industry to highlight the challenges and opportunities that arise from the greater electrification of buildings, including plant sizing, demand management, energy use and storage, and the impact on the wider supply network. It highlights where the new guidance is needed and points to existing best practices and emergent thinking. It can be downloaded from CIBSE Knowledge Portal now, and like all other CIBSE publications, it's free for members. Are you serious about building services engineering and looking to take your career to the next level with professional membership and registration? CIBSE is a professional body specifically designed to building services engineers. Find out more by viewing our short webinar and discuss the different routes to professional membership with CIBSE for those working in building services industry, and the many benefits and the building services resources, both locally and internationally, available to members. You can also speak to me or book online meetings with CIBSE NZ or NZ regional managers to discuss the best membership route for you. You can scan a QR code or visit cibse.org.au and click Join CIBSE to find out more. Finally, I would like to acknowledge Connexus Recruitment for their support of CIBSE ANZ and NZ annual program for technical events. Connexus is a boutique recruitment consultancy dedicated to ANZ's design and construction sector, with over a decade of combined experience recruiting exclusively within the space. The consultants are among the best in the industry and are proud to have connected and talented individuals across the globe with some of Australia's and New Zealand's most recognized consultancies. They are advocates for people and businesses in their journey to professional success, striving to bring back a consultative approach to the recruitment market. The key disciplines they recruit include building services, digital engineering, and project management. Right, reminder and some housekeeping rules for the session. Use a Q&A box for any questions, and these will be addressed at the end. A recording of this webinar will be made available at cibse.org.au in a week from now. I would like now to introduce our speaker for today, John Brock, General Manager of CAMFIL. As some of you might know, this presentation was planned in person, but due to COVID, we have moved it online. So on that note, over to you, John.
Thank you, Rightus. Thanks, Sharon. So there's a little bit of maybe a picture of me. I've probably aged a little bit from that photo, but that's okay. So I'll kick it off. Okay, so that should be all up on screen.
Correct.
Hang on, there we go, it's moving forward. Okay, so a little bit about CAMFIL. So CAMFIL is a global business. I look after the New Zealand side of it, and we're probably the largest single filter company in the world right now, single brand. So more than 55 years, nearly 5,000 employees, getting close to $1 million EUROVENT net sales, manufacturing sites across the world. R&D as well across the world, been to a few of these. And in more than 30 countries, we have sales offices. So headquarters is in Stockholm, and most of the sales they do out of Stockholm are international. That's our CEO and president, Mark, met him. So in New Zealand, we've got 24 employees across New Zealand. I won't take too long on this one here. We've got an office in Cambridge and Auckland. We've got staff around New Zealand. What we do really is we provide products, design, build, accredited air testing services. So this is the validation of clean rooms, containment, biological safety cabinets, and we do specialist filter maintenance services. Some of the maintenance we're doing at the moment are COVID contaminated filters. We've been a wholly owned subsidiary of the CAMFIL Group since 2008, but we've been a distributor since well before that. So the key markets we sort of operate really are in comfort, health, biocontainment, food and beverage, which includes also process air pollution control, marine and industrial. Roles I've had in the company, I've been here for a little while, and previously before that in another filtration business, really in particular healthcare, biocontainment, process and air pollution control. The testing side of the business has been instrumental in working in these critical areas. So this presentation is a few things. It's a little bit about the standards per se. It's a little bit about life cycle costing and energy. It's also a little bit about air purifiers and what you can do to, as well as filters to improve indoor air quality in buildings. So there's two key standards here we're focusing on. We're focusing on the ASHRAE and the ISO 16890. The ISO 16890 standard is a global standard. At some point in time, it's expected that it will probably replace the ASHRAE standard. They are very similar in the fine filter classes. So the advantages of this standard are it's global, and in particular, the measurement of the particles the filters are graded to are also globally measured by NGOs and governments. So what are we trying to remove here? So in theory, outdoor air has got a mean average size of 0.08 millimeters. According to the old standard, the ASHRAE one, this is a very old standard, this one, the size of dust they're challenging filters with is 7.7. It's practically not dust. Most of the things in the outdoor air, in fact, more than 99% are less than 1 micrometer. So, real life. First little thing to concentrate on is the type of filters. Most of the filters in the market for a long time have been a coarse synthetic filter fiber. This will be common in washable filters or typically cheap but high pressure drop pocket bags that will be used in air handling units. And they have a large fiber diameter. They're also got a charge in the fibers, and the charge is an electrostatic. It comes with the manufacturer of the media. The charge is either artificially added or it's just part of making the media. Where most of the best performing filters are what we call fine fiber. They have a much smaller fiber diameter, and they will hold a lot more dust based on a given pressure drop. So this graph here just shows roughly, I won't try and over explain it, but what we've got here, this blue line is a brand new synthetic charged filter, which is operating up here, very good efficiency. And then over a period of time, because of the charge, the electrostatic in it, that will diminish over time, as the months go on, the filter loses its efficiency, which is counterproductive, which is dropping efficiency in collection as it goes forward. In comparison, so say this is a coarse fiber with a charged electrostatic media. Some arrows. So essentially it mean on average you can have more than 40% of your air is unfiltered. comparison to a fine fiber material, which is common with many of our products, they will start at a level and they will typically only improve. They will maintain, if not improve, their efficiency. So you don't get an efficiency loss. You get what you pay for, what's on the data sheet. ASHRAE have done a few things. In fact, there's quite a few institutes have done things on COVID and the epidemic. ASHRAE's main recommendation is you should be using a non-charged filter. So under the standards, if it was ASHRAE, that would be a MERV-A, or as we'd like to focus people on, ISO 16890, because those under that new global standards, the electrostatic charge, the filter is rated on the lowest efficiency it will possibly achieve. What that means in principle is that if you were trying to protect the people in your buildings and have a good indoor air quality, you'll be looking for a grade of at least ISO PM150, and which I've just put this here because some people may be familiar with old grades. This is what I call a good F7, because the old standard, this grade F7 is now no longer a grade. But you should preferably move up to PM1 75%, which again would be an F8 or F9 under the old standard. And if you had high risk, you'd be looking to at least HEPA class. So how does this compare? So if there's people in the audience that are familiar with ASHRAE, the ASHRAE grades are these ones here. You'll get commonly you'll get a MERV-8 or a MERV-14. These are sorts of grades you'll see. In comparison to ISO, these are the classes that they will fall under. Now, the way this works is you'll have an EPM1 and then you'll have a percentage after it. And that percentage tells you how much of that particulate matter size that it will remove. So what can engineers do? What can customers do? Well, update your specifications. Make sure you're using ASHRAE 52.2 MERV-A, or easier still, ISO 16890. And EPM1 class is what really people should be looking at for indoor air quality in buildings. What's in the air we breathe? Many different things. We cannot filter out carbon monoxide, carbon dioxide. We can filter out oxides of nitrogen, sulfur, ammonia, VOCs. All of these things can be filtered out. Particulate matter, if we're just for the state of clarifying this, virus lives in the particulate matter column. So the general drive is to focus on the smallest particles for good reason. So, and in theory, the smallest of those particles. And ultrafine down to 0.1 micrometer, nano even below that. To give some perspective on what these sizes are, the general reported view is that the COVID virus size is approximately 0.16 of a micrometer. The smaller stuff is of interest because it's quite often metallic particles, and those can go deep into your lung tissue and then go deep into your brain and other parts of the body. So really should be focused, especially in inner cities, on fine filters. So what happens in the body? So the coarse dust, typically our throat and our nose and nasal cavity, will remove the large things. The smaller the particles get, the deeper they go into our tissues. So PM1, which is the dangerous one we need to focus on, which is also, PM1 is also relevant with COVID and virus concerns. They go deep into the actual alveoli of the lung tissue. And from there on, depending on the size of them, they can go further through the body. So let's focus on this standard here, because this is the key one. This is the global standard. This is the most relevant and easiest to understand. So the benefits of the standard are, we've got recognition because of the particle sizes that the filters are graded on, measured globally, that they translate to filter classes. It's a better standard with better efficiencies and aligned with real-world air pollution. It's also a global standard, and it should avoid confusion between all of the different types of standards there are out there. The benefits for the industry, we've got a level playing field if everyone's using the ISO. We've got innovation. Products are being developed based on real-world particles, and in theory it should eliminate the low performing products if we're going over to the standard. It's one test. It's not multiple countries doing multiple things. It's an easy to understand standard. Once you get the concept of it, it's easy to understand. So this is a comparison of the 3 standards that the filter industry is quite commonly aware of. We have the EN 779 2012, which has been replaced in full by ISO 16890, and we have the ASHRAE 522, which is still a current standard. So how do they compare? The old EN 779 used this size particle, 0.4 micrometer, as one particle size to measure all filters that fell into the medium and fine filter class. The ASHRAE 522 and ISO 16890 use the same particle size range of 0.3 up to 10 micrometer. The ISO standard breaks this down into particulate matter sizes. Now PM10 and PM2.5 are commonly measured around the country and around the world, and they compare perfectly with the new filter standard. The differences in between them are, the discharging method is something to really focus on between these filters. There's an easy way really to understand whether you've got a discharging filter or not, and that is to make sure it's ISO rated. So the old EN 779 had a good discharging process, but was using an unusual particle size. The ASHRAE one is a soft one. It's not and it's not mandatory. The ISO one is again a tough discharging method. It means if you are looking for a greater filter, you can be assured it's not going to drop efficiency over time. And the difference in loading is that the these 2 standards use the very coarse dust that we saw on the previous slide of about 7.7 millimeters, which is typically lighter, and where the new standard will use a fine dust, which is more relevant with what's in outdoor air. So the difference here is that we have gone from 9 classes to 49 classes in 4 different groups. But the reality is that manufacturers are not going to make 49 different classes of filters. There will be a set group of them that will be made. So the difference here really is in the way the filters are discharged and the size of the particles used. So salt is used to generate the larger particles for the test, and oil is used to generate the finer particles. So the discharging method is basically isopropyl alcohol, and that will reduce or eliminate the electrostatic charge in the filter. It doesn't damage the fiber of the filter, and you can remove all of the charge. So there's some simple rules with filter classifications. The efficiency of the filter is always the average between the initial and the discharged. But to be able to report based on the ISO standard, you need to meet at least 50%. And in theory, that what we'd have here is if people were using an F7 filter in the old language, that now would be an EPM1 50%. So that would broadly mean it would remove 50% of 0.3 to 1 micrometer size particles. This shows how many grades there potentially could be, and there'd be more because of the coarse class also starts in 5% increments. But manufacturers will not make every 5% increment. We'll quite find that you'll get a 50, a 60, a 70, 80, and so on. But essentially, they all have, you can't get a filter that's rated, you won't get an advertised filter rated as EPM 150 as well as EPM 2.5 at a higher percentage. They will always fall on the smallest size particle. So if the filter is good enough to make 50% EPM 1, it will always be rated EPM 150. So the focus here really is on the different sizes of particles from the PM1, the different dust loading, and the different the tough discharging method, which means that you know your filter is not going to drop efficiency over time. We focus on the smallest things we can see with our eye. They would typically be 50 micrometer, and the filters we are focusing on are at least 50% at 0.3 to 1 micrometer. So you cannot tell with your eyes whether you've got good filters. It's not possible. And the comparison obviously is quite huge when you look at it like this with a whale and an elephant and a person. Summary. Okay, so the research really proves that the PM1 particles have adverse health effects. And again, we can put COVID in the same group as PM1. And the reason we can do that is while the virus might be approximately 0.16 of a micrometer, the aerosols and the droplets that are carrying that virus will typically be half a micrometer, if not a little bit bigger. WHO has new guidance. They did have higher values for micrograms per cubic meter of air, and this is how New Zealand government and other NGOs measure this. They were, I think, twice this level before. They've now brought it down, they've now halved it, and that is a maximum level. We have some particulate monitors, and in New Zealand we can see quite a range. We've seen between 1 and 25 micrograms cubic meter. It's easy enough to look this up online, but and that's for PM 2.5. Remembering they don't measure PM1 at the moment, but Auckland City would typically be around 5 to 10 micrograms per cubic meter of PM 2.5. So we're right on the level in outdoor air of what you're allowed. The ASHRAE test can be confusing. It's a statement here. So the ISO standard is the key one to focus on. The old filter standard EN779, this was the G1, G2, right up to F9, are not grades anymore. You should not be getting filters with those grades on them. There's possibility that on a very coarse filter, it's acceptable to have a G2, G3, G4, but anything in the medium and fine should be ISO rated or ASHRAE rated. So these are no longer grades. If you get teams of people saying we're going to replace our G4s or F7s, we should be saying what ISO classes are those. It really brings a lot closer to the testing in the real world, what's happening, and also the government NGO reporting of air quality. So it's directly related now. You can get a filter that is directly related to what's being measured, probably not far away from the site anyone may have. The REVA guidance really for improving risk around viruses and indoor air quality is EPM 170 minimum for recirculated air and EPM 150 for outdoor air. So old language, this is a F8, a very good F8. Again, you can't just state you need an F8, that's not how it works, or EPM 150 for outdoor air, which would be a very good F7. So really, the key advice is to include ISO 16890 in any filtration specifications. Okay, that is the first part. There's another part. So I've got some Q&A questions here that they have already answers on them, so no one needs to try and ask me any questions. So MERV, what does that stand for? That stands for Minimum Efficiency Reporting Values. So that is once it's been discharged, that's the lowest you're going to get. The percentage of particulate in the air in the fine category, I think, is 99. Again, so this is most of the stuff in the air is in the fine category. The type of dust used to load a filter during testing is typically ASHRAE test dust. PM1 is particulate matter 1 micrometer and smaller. And the average diameter of outdoor air, I think, is 0.08 of a millimeter. Coarse fiber filters are have an electrostatic charge to pass the ASHRAE test, and that electrostatic charge is something we need to avoid. Next one. Okay, so what happens to a coarse fiber filter when subject to normal outside air? The efficiency will drop. It's because once the fibers get insulated with some dust, moisture, many things, the filter will drop its efficiency. MERV is the conditioning step to ensure that you know the filter is, you know the minimum you're going to get out of the filter. 16890 is the new global standard for testing of filters. And the 4 categories of filters that fall into the 16890 class are coarse, ISO coarse, PM10, which is 3 to 10 micrometer, PM2.5, which is 1 to 3 micrometer, and PM1, which is 0.3 to 1 micrometer.
Excuse me, John, just to interrupt you for a second. If you could please maybe speak up a little bit. Occasionally the audio becomes pretty faint.
Oh, okay. Sorry about that. Yep, thank you. Just sing out if I need to again. This slide here is about air purifiers and air cleaners and a air quality inspection report done at a site. This is a bit of a hot topic, air cleaners and air purifiers. Now the guidance really again is the same as WHO. Here's our maximum recommendations, 10 micrograms per cubic meter. And this is the lowest level that they think lung cancer and mortality will increase. We should be aiming for less than this. The testing was done, this is I think it's an Italian test from memory, and the daily average in our area was 9 micrograms per cubic meter. So just under the WHO's maximum recommendation. This would not be too far off what we would see in Auckland City. To focus on on air purifiers, it's important to make sure people understand that there's two mechanisms. We have source capture, which is this guy over here, where somebody's going to get their teeth worked on, and then we have dilution, which is an air cleaner sitting in a corner, pulling in air and pumping out air. And of course, there'll be some re-entrainment going on here. It's just the nature of these devices. The reason for air purifiers, ultimately the HVAC system can quite often not deal with the loading of people, and you may need some other type of scrubber device in there to scrub basically aerosols and droplets from people. So this case study was this type of air cleaner here with a particulate sensor, and measured in 15 minutes and 1 hour post installation. So in this installation here, we didn't actually have too bad a level before the test, 1.3 micrograms, but the air cleaner dropped it to 0.3 and operated fairly quickly too. You know, we can see here in minutes, it's pulled it right down. Outdoor air, meanwhile, was closer to 4 micrograms. There's another example, this one here. So this again, it's pulled the levels down inside the room by running the air cleaner. There's a few of these case studies, but this is probably the second to last one. Essentially, there's plenty of proof of efficacy on using these devices, but the principle really relies on the type of filter it has in it. There's a lot of commercial ones in the market that say HEPA on the box, but they're not HEPA. The key things come with air cleaners, and that is to make sure the filter is individually scan tested and rated to the correct standard. So the number of locations were tested in this one here, and the results were overall, it made a very good difference to the air quality for PM 2.5. PM1 level would also be very similar. The filter in those devices is 99.995% at 0.15 micrometer. So if you didn't want to use that, or you had split systems, you just had ventilation grills, there's no way you could upgrade the system. These sorts of devices are very helpful, and we're selling a lot of these now, hospitals obviously for COVID, and they just can complement a split system, and they'll do about 700 cubic meters per hour. So these sorts of devices are out there, and they're basically plug and play and can complement a split. This would have a H13 or an H14 HEPA in it, and a booster fan. Yeah. If that doesn't work, there are portable devices. So that's enough of a little sales pitch there. Now, the next part is about energy cost and the particle efficiency. If we're all agreeing that we need to have finer filters, then we need to consider how much it's going to cost. Filters are a bit like light bulbs. They've evolved. They've started down here, and they have just steadily got better over the years. So in this example here, this is a common filter you'll find in many buildings. It's a washable panel, may also be just a throwaway panel. And the pressure drop this filter would consume, all filters are rated for this flow rate, 944 litres per second. So this would consume 110 pascals. It's only going to remove very coarse dust. As we've evolved over the years to what we are really selling to more premium buildings, hospitals, museums, very good indoor, good quality office blocks, we have dropped the pressure drop and we've gone up into the PM1 filter class. So as energy costs money, these much better filters actually cost less to run. The way it's easy to understand too, people don't have to go and stare at the pressure drop of the filter at the flow rate and the EPM1 class. They just need to know the PM1 class they're looking for and try and choose the highest energy class that they want to use. There would be probably a logical reason to use some of these lower classes, and that would be on systems that would be not operating very often. They might be doing 3,000 or 4,000 hours per year at best. These lower energy class filters would unlikely be a problem there. So how this works is they define limits for kilowatt hours per filter class on average per year, and this is a standard. So manufacturers sign up to this energy program. So if we looked at those, this is a comparison of filter efficiencies similar to that previous slide. We would find that if we were going up to HEPA H13, which this is another ISO standard, but this is 99.99% at 0.3 micrometer. Or 99.95 at 0.15 micrometer. Remembering COVID is approximately 0.16. We're almost 100%. It's just the efficiency is there across all flow rates, all particles. If we looked at if we were recommending a filter for medium level of protection against COVID and virus in a building, we would be looking at this class here, EPM1 80%. And we can see here that it actually has a very good efficiency for 1 micrometer upwards. And given COVID potentially is living in a 0.5 micrometer upwards, aerosols and droplets, the risk is still where there is some risk, but it's pretty low. We've got some very good efficiencies. And then you drop back to coarse filters, which you quite often find in buildings now. The efficiency down here for COVID is practically nothing. So this is a comparison between 2 types of filters using the same type of, this 2 here are the same fiber, the same filter class. It's quite simply that the filter with the most number of pockets, which is an A+, will use a lot less energy per year. If we equate that down to what that costs, it's often as much as the filter costs itself. So there is a perfectly good reason to upgrade filters to high energy class filters. This is a total cost of ownership calculation, a few slides. This one here is just a small HVAC system, 10 filters running pretty much 12 hours a day, every week of the year. We have a calculation system we can plug all this into. We're consuming the outdoor air is reasonable, and we need good indoor air quality, and it's just a single filter and over 3 years. So what this shows is the difference in the filter pressure drop between 3 models. We've got a panel filter, which people are using quite often now for comfort air in buildings. And then we have a very basic pocket bag, and then we have the premium A+ energy class filter. So most of the energy cost comes from the difference in pressure drop. Also clean, but also over time as it loads. So in this instance here, the premium filter is a lot less pressure drop than the basic filter at the standard flow rates. You can see a big difference there, going from 60 to 110. So that's all energy right paying there. In the terms of particle efficiency between those filters, the very basic filter will have 6% efficiency per PM1 particles, and the correct grade filters for decent indoor air quality, say F7 minimum, which is EPM 150, we're looking at these sorts of efficiencies, 57, 62. As we go up in the particle sizes, the efficiency improves. So panel filters are removing hardly anything of outdoor air. They're only removing things you can see. If we look at the total cost of ownership, again, this is 10 filters, 3 years, what that works out on over time. The total cost of the filters, the energy, and the labor, the premium filter works out cheaper than the cheaper filters. It's just basically primarily based on the energy. And then this explains how that happens. Ultimately, the premium filter, which is the light blue line here, will have a very slow and consistent pressure drop increase over time, right up through to plus 9,000 hours. The cheaper filters that don't hold a lot of dust, the pressure drop will go up quickly, then they'll change, and they'll just repeat the same trend. And this darker blue line here would be pretty much what the market is generally using. As I say, there are exceptions, but most buildings will have a very basic filter like this blue line here. So there are improvements that can be made based on pressure drop here over time by going up to a class A or A+ energy filter. The other benefits, obviously CO2, which is directly related to energy, and we can report on that, but there's benefits there because of the energy difference. And again, the energy consumption, just as a separate slide, what happens with a cheap, low efficiency filter that uses a lot of pressure drop versus a premium high media filter, it's got perhaps 10 square meters of media or more, the energy cost is vastly different. Okay, so solutions to clean the air. The general guidance is we need to increase the amount of supply air into the building, so outdoor air. That's especially relevant with COVID. Should be using, for the outdoor air part, assuming this was just a fresh air handling unit, should be looking at EPM 150% or better, which would be MERV 14A at least under the ASHRAE. The recirculation air should, in theory, be a bit higher due to COVID and the chances of aerosols making its way back through the system. Should avoid unfiltered recirculation, which is very hard to achieve with fan coils and split systems, which practically have no filters, and upgrade to EPM 170 or 80. And if none of those things are possible, that's where you can start considering air cleaners. Some of the guidance documents and standards we look at are here. I mean, the WHO has got some very good information on particulate matter, but also gases that people should be focused on: ozone, sulfur dioxide, oxides of nitrogen, and others. REVA has come out with some very good information on how to protect how to deal with your systems due to pandemics. VDMA around process equipment, of course EUROVENT and VDI. VDI makes very good recommendations on hygiene for the HVAC system. The EUROVENT standard, there is if somebody said, how do you select a filter for an application? The EUROVENT 4-23, which I think is now an ISO number, that makes some recommendations. So it would typically say an office in a big city, you should be at least EPM 150 to 60%. And if you're a hospital in a big city, you should be 50 right up to 80%. And again, with the guidance from REVA, EUROVENT, and others, they are recommending EPM 180% for recirculated air handling systems. And they make no change in recommendation for outdoor air because the risk of viral load coming in outdoor air is extremely low. Thank you. If there's any questions, I can take it over to you, Otis. You can go from there.
Thank you, John. Yeah, so currently there is one question, but feel free to write these up, and I'll read them out for John to answer. So first one is, could you please elaborate on how the filters mentioned in this presentation not only don't lose efficiency but become more efficient over time? That's from Alex.
Yeah, so the filters that lose the efficiency over time are the ones that rely on electrostatic charge on the fibers that attracts the small particles, and that charge diminishes over time due to a dust cake, moisture, could be ozone, VOCs, could be many things, and that charge will diminish. But otherwise, normally, a filter should improve its efficiency slightly over time to a point. So a mechanical-based filter, the efficiency should be stable and in fact improve over time. I'm not sure if I've answered that quite right, but that's yeah, the focus really. The electrostatic will go down. Mechanical filtration, fine fiber, not using a charge, which is as per the ISO standard. You can only expect it to improve over time.
Right, we have another question. Are pre-filters, i.e. COARSE G3, still useful in preventative bag filter life in performance? I've
got two views on that. I think if you're using, if you had a system doing 30% of outdoor air or higher, you possibly should consider pre-filters, or if you had high lint loads in your system, you should possibly consider pre-filters. But the pressure drop of a G3, G4 panel is quite often in the order of 75 to 120 pascals. versus the fine filter being 65 to 100 pascals. So it doesn't make a lot of sense to put a pre-filter in systems, especially a washable. It makes very limited sense. So the two things are lint loads. You may need to look at those, or consider a fiber that will deal with lint quite a bit better. But no, I think pre-filters are overused.
Awesome. Right, there's another one. So, question from Vlad: is there an organisation that does independent filter testing and certification of performance?
VTT, there's a number of them. Yeah, VTT is one in Switzerland. I'm not aware of any specific company or in Australia or New Zealand. It's VTT, Blue Haven, Australia and America. There are others, but proper manufacturers. We have our own validated test rig. You can be approved to do your own testing. So we've got a combination of our own testing, and we've got a combination of independent reports. The thing I would say though is because of the way the new standard is, which is based on particulate matter, 0.3 to 1 micrometer, it also means now that if somebody was wanting to check the efficiency of their filters, you can actually use particle counters now, because particle counters will count 0.3, 0.5 and 1 micrometer. So you can actually, if you had a fine filter installation, you could measure using a particle counter before and after, and you'd be able to tell whether your filter is broadly meeting the data sheet that it comes with.
Awesome. Do we have any local guides in ANZ advising the ISO filter grades most suitable for various applications and even cities and locations?
In Australia, sorry, ANZ meaning Australia and New Zealand?
Yes.
People recommending. Well, I think Becca's got some good stuff in their standards now. I know other consultants have as well. So there's been a good shift with the consultants to the new ISO standards. So I think you'll find that if the reputable consultant firms should know about this. CAMFIL is also, we're also happy to help. If people just want some guidance, no obligations, we can make some recommendations.
Do you have any comments on UV filtration for AHU and vent systems?
UVC. So I've got what I've read about it is yes, it's a technology that can work. But there's a certain dwell time over the tubes that needs to be maintained, and then the tubes need to be replaced at regular intervals, which I think is about 8,000 hours. So it's quite often a very high cost, very high investment for something that will reduce efficiency over time. And if we look at the guidance documents from River and others, they are primarily avoiding those technologies and just stating you should be having a minimum efficiency level of your filters. So yeah, it's a technology that works, but I think it's also not required.
We'll just give a couple more minutes, see if anyone else has any more questions. It's definitely been interesting to learn.
Yeah, look, it's been a very interesting last few months of mad panic to upgrade hospital systems, install air cleaners. I'm just conscious that there's no magic bullet here with this COVID virus. It's about dilution. It's about air change rate. It's about having enough fresh air coming into the buildings, and then the rest of it is what people do, how close they are, all of the other things, washing your hands. So air filtration definitely plays a big role, especially areas that there's minimal amount of air movement. There is an ASHRAE standard 170 which gives guidance for healthcare primarily, around air change rates, and that's typically been adopted for hospitals. There's quite a bit of learnings in that for public buildings, private buildings as well. It should be looked at. So
do you see a big shift in landlords looking at their commercial buildings and being upgraded, just to make sure that you get peace of mind for people going back into the offices?
Well, I think there should be a big shift. It's because it actually can be a selling point as well for tenants, for customers that may be using the property. If people are, if the owner of the building is focused on the fact that it's got PM1 filtration, so I think people should be shifting and becoming more aware of it. Around the world, it has shifted. Australia, New Zealand here, we're a little bit behind. The hospitals have jumped really quickly, but we should see an uptake with private buildings.
Got another question. Could you please? Oh, okay. Yeah, the recording will be online, so it's will be available from a week from now. So if you missed it right at the start, it will be available from cibse.org.au. So yeah, if you're a CIBSE member, it's free to view again and yeah, have a copy of.
No, excellent. Thanks, Radis.
I guess, yes, since there's no more questions, well, thank you very much for your time and knowledge and sharing with everybody. Much appreciated. Yeah, so, and hopefully we can do another event like this sometime, maybe next year or something, once we move out of the COVID and see what the outcomes were.
Yeah, no, you're welcome. I think it would be nice to have, we didn't have time for case studies today. We've got a few of those, some real world testing, the differences, especially with particle counting, and bring a little bit of what's happening over in the clean process, clean room, GMP environment, colony, they do microbial sampling. This is all very relevant now with COVID.
Yeah, which would, the case studies will actually show it what was before the COVID and what you've done now. So yeah, much more relevant, like you said. So
yes, yes, yeah.
Awesome. Right, thank you very much. Thank you everybody else who attended, and I hope to see you next time, hopefully in person. So we will be kicking off with our seminars probably next year in person, but obviously provided we have a location that's safe for everybody to attend. We will be trialing doing it online and in person all at once. So with a live stream. So for those who feel a little bit uneasy about coming to larger events, but it should be good. So looking forward to that. On that note, thank you very much, and have a great evening, everybody. Thank you, John.
Thank you.